On the call, my whiteboard. All right, so done. I'll copy the link. I see Raheem as the only person who has seen my whiteboard link that I've shared so far.
Yes, sir. I clicked it too, but it says access denied. So I sent a request to join.
Yes, sir. Same.
For that, as I said to you guys, I'm still at work, so my desk goes. All right, so the chat. Actually, paste it again. The chat, the whiteboard, and see. I'll look to see if I can give access. Not seeing an email coming up as yet requesting that. Okay. So more people should be joining. Please let me know if you're receiving access now. Gaining access to the whiteboard. Stuart.
Okay.
Matthew, you said that you had problem. Are you there? See my whiteboard now?
Yes, sir.
I'm there too, sir.
Absolutely. Thank you for that. Thank you for that. So between my whiteboard and my videos, we're gonna use that as our teaching tool. All right, or should I say my sharing tool?
Sir, I haven't been granted.
Back.
Yes, sir.
What is it saying?
It said access denied, and then I pressed the access to get access, and it says you'll get an email if your request was approved, and I haven't received an email yet.
Try refreshing.
I just click the link again and it'll come up.
Okay. Okay, came up now. Thank you.
All right, I'm seeing 13 out of 20 people, so there's some people who still might not have. But be that as it may, so what I did last week was, and I do not have. I'm using my mouse, so please forgive me if my drawing looks like kindergarten. All right. So we have the S and the R as our inputs, and we have our output of the Q and its inverse. Right. So that's what it looks like. And based on what we did last week, we said that this inside here is a black box that makes things happen based on the truth table that we developed. Remember? Remember, we developed a truth table and you said that, confirmed before that that was good. Obviously, there's one um, value that is not seen here, but it is assumed that what happens here is that you have an output. Q is the output that happens after you have done something to the inputs. But the output that we looked at last week was Q plus. I call it Q plus, which is the input, sorry, which is the output prior to us doing anything to the inputs S or R in this case. Show you the truth table, how we developed it. And one of the limitations that we mentioned was when both S and R are activated simultaneously, the output of the flip flop is indeterminate, right? And therefore, we don't want to be in that position because you can see we need to be very clear that the system is working. We need one way or the other to know that the system is working, right? So, what is done? Could you hold on a second for me, student? And everybody, everybody. Yeah, man, I'm actually doing some online teaching. All right, I'm so sorry about that. Are you still hearing me?
Yes, sir.
Okay,
Yes, sir.
thank you for that. Now, so we know that we don't want, and this is one of the limitations of the SR flip flop. When both inputs are high, the output is something that you are very clear on. And we don't want that at all. We want to make sure that the system is functioning as how it ought to function. That is what makes things, even if it's not working well, at least you know what it's supposed to be. So we make sure that if that system is not working, we know, well, this is what's happening, why it's not working, and we can fix it. With the SR flip flop, when both inputs are high, it provides that limitation. It does not work well. We don't know what the output is going to be. So, what is critical for us is to now make sure that we overcome this limitation for the SR flip flop. And that is how we come up with the JK flip flop. It's the very same flip flop. Again, my apologies if my drawing is not all that great. I don't have a style that I'm using, but Hope you bear with me. So the JK, and yes, we still have the output being Q and its inverse. The only thing that happened that makes the SR different from the JK flip flop is that you do not have the limitation of the SR flip flop. The JK doesn't have it. The JK flip flop, when both inputs are the same, well, are high, when both inputs are high, what happens is that it provides or perform what is called toggling. Toggle. So toggle means that if it was when both inputs are high, if the output initially was a one, and then the system gets both inputs to be high at the same time, then it means that that output toggle are changed from that zero to a one, and vice versa. So if initially the output Q was one, and the input J and K now becomes both high simultaneously, that output switch from being that one to a zero. So that's the difference. So remember the SR flip flop, that doesn't happen. You actually do not know what the output is going to be when both inputs are high. Otherwise, the SR and the JK flip flop are identical pretty much. All right? Are we clear on that?
Yes, sir.
So, as it relates to the truth table, what I can also say is that for the truth table, what you will have in the very last, and I'm going to run the video because I want you to watch the video. In the very last column, or rows rather, when the inputs are high, the SR input output rather is unknown, so undefined. Really, we don't use that. But for the JK flip flop, the output when both inputs are going to be zero for the last rows in the truth table, it's going to toggle. And remember, ladies and gentlemen, toggle means if the output initially was high, the input is and the inputs are the same. Well, in this case, both inputs are high. Then the output is going to be no move from a one to a zero, and vice versa. If initially the output was zero, Q was zero, and you have J and K being high, then that output now toggles from zero and becomes a one. So that in this case, you are very much aware that you know what the output is going to be. Whenever you see a toggling, it means that both inputs are high. Good? That's the trademark of JK flip flop. And then we have another flip flop, which can use either the JK or the SR flip flop. Normally, it's the JK flip flop that it uses. And that's what is called a D flip flop or the data flip flop. So it says J, this is K inputs. So these are inputs J and K. I want to know we have the output Q and not Q. And as I said before, what? This is the same as the SR flip flop, right? Only that we use this more predominantly because we can predict what the output is going to be. We use the JK flip flop more than the SR flip flop. So as it is now on my whiteboard, this would be just regular to this with the JK flip flop. But with the D flip flop, what happened is, and it stands for data, there's a situation that is set where at no point in time you can have the input and the output, the inputs being the same. So J can never ever be equals to K. And the only way we cannot guarantee that that is the case is to do what? You see my screen?
Yes, sir.
On my whiteboard?
Oh, no.
Yes, sir.
So what did I do to make the case that I mentioned that J and K can never be the same?
With a not, sir. Or invert.
Put an inverter.
Yes, sir.
Oh, you guys would see the inverter. So put an
Yeah.
inverter means that J and K. So this is the data that's coming in, and this is called the D flip flop. So this is called the data in. And what happens is that the data in will always be the same as what's on J. So whatever is on the data in is your J. So this is the D flip flop. So in a nutshell, the D flip flop. What we know is, ladies and gentlemen, we cannot have the situation that happens happening with the D flip flop. Why is that? Well, the limitation that we have with the SR flip flop cannot happen whilst we're using the D flip flop. Why is that? Somebody can tell me?
J and K wouldn't be the same at any given time.
Absolutely. So, what we know is that we cannot have both inputs being 0, 0, nor can we have both inputs being 1, 1, because of this inverter that we place between J and K, or S and R. So you never have the situation where the inputs are the same. So it eliminated from our initial table that I gave you last week. It eliminated 4 rows, the 2 top rows and the 2 last rows from a true table. So you only have the four. All the possible conditions would be the 4 middle rows. So if you look back at the notes last week, you realize that that's a big difference between the J K flip flop and the D flip flop. All right. So armed with that, we can look at something else. So there's one thing else I need to tell you. As it is right now, ladies and gentlemen, we're looking at what is called asynchronous flip flop, which means that it doesn't need, so any one of these three, they actually um don't need, they don't use rather any form of clock input to synchronize the working of the flip flop. If we use the JK, if we use well, anyone, JK, SR, anyone that we use, we can actually um, put a timer on the circuit to make sure it works using a clock source. And right here is where our clock source would go. If you're looking again at my whiteboard, that's the symbol for the clock pulse. That's where the input clock pulse. Now, a clock pulse is like the gate of a system. So you can put right here as a clock, right? So the third input would be CLK for the clock. CLK. So each of these have a clock now, eh? Input CLK. So last week, you remember we used a scenario about coming into the classroom and we look to see we have 2 doors, right? So that's a clock pulse again. Each of these have a clock pulse. And these, of course, are now called your synchronous flip flop because they're depending on a clock pulse. The clock pulse, as I say, is like the key to your door. So you and I know that if we come into the room and we look at it, if we get into the room and we look at the situation where the light is off, and we apply a set situation by turning on for the SR flip flop by turning on, putting a 1 on the S and a 0 on the R. or a 1 on the J for JK, a 1 on the J, and a 0 on the K, we know that we're going to set the system, right? Where the initial output was off. But that can only happen, ladies and gentlemen, if you get into the room. Make sense? Make sense?
Yes, sir.
Yes, sir.
But if the room has doors and the doors are locked, you must, before you can actually turn the switch is on to either set or reset. You have to get in, right?
Yes, sir.
So the clock pulse is like the door, the key to the door. You have to open the door before you get access to the S and the R or the J and the K inputs. So the clock pulse must be present and active to open the door in our situation before you can turn on the switches to have a set or reset. So that's why I said that's what a clock pulse is. So some clock pulses requires a 0. They call it an active low. So you have a 0, so it's like an inverter. You need an inverter. You put a 0 on it. There's an inverter that changes and cause the system to open the door or cause you to have access to the inputs now. And there's some clock poles that are active high, which means that there must be a logic 1 present at the clock pulse before you can activate the input signals, S and R or J and K. Am I making sense?
Yes, sir.
All right. We go back to our situation. If it's an active low clock pulse, and I'm going to use just one of these diagrams of the 3 to let you understand what I mean. If it's an active low, what usually happens is that there's a bubble, a little bubble, that is placed right at the entrance of the clock pulse. So I've done that for the JK flip-flop on the whiteboard. So if you see a little bubble like this, it means that the clock pulse must be low. And when the clock pulse is low, that's when the door is open then. That's when you can now apply the input J and K to activate getting an output. For the other flip-flop on my whiteboard, the SR flip-flop, this is active high. So it means that there must be a logic 1 to, as I proverbially call it, open the door to allow the signal or the inputs to be activated to cause the output to change. So are we clear on what is input low, a clock pulse, which is active high and active low?
Sir, could you repeat about active eye, sir?
The active high just means that you don't need a logic 1 on the clock pulse. So the clock pulse must be at a logic 1, meaning that's a high. So whenever the clock pulse is 0,
That's a
it means
low.
that the inputs and the door is closed. But when the clock pulse is 1 for the active high, when the clock pulse is 1, it means that the clock pulse is saying, okay, now you can get access to the input switch S and R to turn it on.
Okay,
For the
sir.
active low, it needs a 0 on the clock pulse. So the clock pulse must be 0. So remember the clock pulse. So a clock pulse is really just a chain, a pulse. So as I said again, let me undo this. Let me erase this. And that doesn't look like a. All right. So my clock pulse that I'm adding here. So this is my clock pulse. Set of 1s and 0s. Okay. Now, if we were using, are you seeing my clock pulse? Just to confirm, please.
Yes, sir.
Good. So what we mean by that is that only the negative are the zero. So only when we are here, the clock pulse. So this clock pulse that goes into it, only on these. So when it is low, that the clock pulse give it access for the inputs. So when the I, the door is locked. So meaning that the inputs cannot you can't access the input to send them to the output. That's what we're talking about active low. If you have a clock pulse again, similarly over here, a clock pulse. Active high just simply means that it's only so notice it's only the rising edge or the top of the clock that is causing. So there's only when it's a one, the clock is going to give access to the. That's what we mean by so these are clock pulse, of course, CLK. Right? That's what we mean by that. Now, if you understand that, then we can move on. Please let me know if there's anything else that I need to elaborate on or explain. Cool with that?
Yes, sir.
All right. Now, one other thing that I want to let you guys know, and that is there are a few more inputs on two SR. Sorry, a flip flop. There are some special inputs that are usually a part of the package of how the flip flop is manufactured. You have what is called a clear, and again, CLR. So for those who are able to see my whiteboard, it's CLR. Oops. Which so you can put a clock pulse to clear. What am I clearing? I'm clearing my output. That's what clears means. So whatever was on my output, I'm clearing it and resetting it to zero. So like when you have a calculator and you hit that button, the C button on the calculator, and everything goes off, right? Anything that was there, clear back to zero, right? But that's what a clear button stands for. And of course, every one of these have their clear inputs. They can apply a clear. Again, you can have flip flops that has high clear, meaning you need a one to clear it, or a zero to clear it. If it's a zero that you're using to clear it, then it means that it has a bubble right here, right at the, right. Another important input that the flip flop has is what is called the preset. Preset. One second, guys. Henry? I'm sorry? Actually, I'm doing a class online. I'm teaching. Well, if I'm representing him, I'm signing on anything that needs to be done. All right. So, okay, man. Sorry about that, class. So this is the other input that is, and again, sorry for my writing. It's called the preset. So it's a preset. What does that mean? It means that before I apply the clock pulses, I can set my output to whatever value I want. I can preset it. Good? So I can put values here on my output of ones and zeros, or one or zero. Now, always remember, ladies and gentlemen, that one of these only store one bit at a time. And the one bit that it's stored is usually on the Q output. That's what is stored. Okay? So now we recognize that we have quite a few inputs that are useful and going to be useful in our utilization of or the application of you are using the flip flops. Any questions? So we all have clear and preset inputs. Okay. And just always remember what the inputs, what these are, okay? What they serve for, the purpose. Any questions? And please feel free to raise your hand or whatever you need to do to be recognized if you have a question or a concern or something that you just need to have clarified.
Sorry. Can you explain why the preset is used again?
The preset is that you can use a preset input to set the value of Q. Let's put something on the output Q before you actually apply the input. So remember, whether it be the clock pulse or the J input or K input or S input or R input, anything to the input, you can actually use that and preset or store. So it's like you have a calculator and save something in memory. And then you're going to do a calculation and recall what was saved in memory. So putting that in memory is a presetting. Clear on that?
So thanks.
All right. So let's look at a short video. Well, I'm going to give you a longer one. But we'll do it together for the purposes of understanding. And by the way, for those of us who are here, I'm not going to keep the entire session. I know some people would have normally run to a next session, but we don't have that session to run to today. Is that the case? So we're going to have a little longer than past 2 o'clock, but we're not going to go all the way. All right. So let me share with you this video. I haven't put this one as yet into the Google chat or the Google Classroom. So let's see. Please let me know if you're seeing my screen with the share. What to
Yes, sir.
All right. So again, it's just about half an hour. We will take it in pieces, and you can let me know where you need me to stop. All right. So sit back with your note and take note of flip flops generally. Oh, by the way, I should also tell you that in some places and some cases you see it's called a latch. You see called a flip flop. A latch is really the flip flop without an input clock. All right. Once you have an input where you have clocks and all that, that now becomes a flip flop. So the latch, what it does, as the word say, is latch on to what you change you make on the input at the output if the condition permits. But the flip flop, you'll change based on other inputs apart from just the input on S and R or G and K, right? But also from your Q output. All right, so here we go. I'm going to mute my mic when I'm playing it so that you don't have cross. But if you have any questions, please feel ask. I'll start the video. Am I clear?
Yes, sir.
And then we're disabled, so we're going to hold.
Let's start, but from beginning.
In this lesson, we're going to discuss flip-flops and what they do and the different circuits and the truth tables and timing diagrams associated with flip-flops. So flip-flop started out with the SR flip-flop, the set reset flip-flop. And they started out by just making them out of NAND gates and NOR gates. And we'll look at the NAND one next. And the cross-coupled NOR was one of the first ones that were ever made. And what a flip-flop does is, if you looked at the lecture notes, you see that a flip-flop actually stores a binary piece of information. You can either store a high or store a low, kind of like a little memory address in like a computer, but it only holds one bit. And what we can do with that is we can keep it stored there or saved there either until it gets changed or until power gets removed from the circuit. So one of those two things is the only things that's going to take away that setting. So let's look at this SR cross-coupled flip-flop. Let's make a little truth table for it. So we've got S, we've got R, we've got Q, and Q naught. Now remember, Q naught should just be the opposite of Q. It should just be the inverse of whatever Q's doing. So we've got 0, 0, 0, 1, we'll count a binary, and 1, 1. Now, when I go through this, I'm not going to actually do it in binary because you'll see why it makes more sense. But I'll show you what mode it's also in. So let's start out by setting high on a set and a low on the reset. Now this particular flip-flop is what's called an active high. In other words, it takes a high to activate that input, or it takes a high to set this flip-flop. There's also ones we'll look at later called active lows that take zeros to activate them. So in this case, there's no inverters out here, there's no bubbles, so it's an active high input. So what we're going to do is a high, low on reset. So a high on set, a high going into this cross-coupled NOR, into a NOR gate, a high into a NOR gate. If you kind of think of it as an OR with an inverter, if it's an OR gate, any high gives you a high out, right? So 1 into the OR gate gives you a 1, inverted to a 0. This 0 is getting fed back here to here. 0 or 0 gives you inside, like I said, just an OR.
All right, so I stopped the video because I wanted to make sure that you understand something. So you remember, as I just showed you in the whiteboard, on the whiteboard, that we have some block boxes, right? Are you hearing me, guys?
Yes, sir.
So consider these as input as what's in the block box. That's the first thing. So remember, we have a S and R and input, and we have a Q and not Q, right? Output, right? Good. But we never see what was causing it. So inside, this is the SR flip-flop made with one of the universal gate, which is a NOR gate. So with a NOR gate, SR flip-flop, there are only two flip-flops. You notice the NOR gates? Two NOR gates. But look at what happened. There is what is called a cross. A crossing input. So the output of Q goes to it becomes the input at the S, and the output of not Q becomes the input at the R. All right? No, ladies and gentlemen, whilst this narrator does not speak to it, always remember that the real thing is, where do we start? What's the current state of the output? So while we have this crossing of Q and not Q to become part of the input, remember, we cannot have a one input OR gate or one input NOR gate. We can have one, but we have to, if that's the case, we'd have to do what? We'd have to have both of them being tied. to a one, right? Or to that one input. So in this case, you must have two inputs that goes into a NAND gate or a NOR gate, which are your universal gates. So in this case, it's getting the input, one of the input from S, but the other input comes from the cross of the output of the other NOR gate, and vice versa. So this that is here is just the black box. So and what is happening now is that they're just populating only the four conditions. When they are S and R are the same, when S and R are different, and when S and R are high. So when they're same low and when they're same high and when they're different. Four conditions. We use 8 conditions in setting up our truth table because we know that, and I showed you last week, that the truth be told, if you do not have anything that's happening, so if we're a case where nothing is happening on the input, where in this case there's 0 and 0 for the inputs, but you had the output being either a 1 or a 0. So we use those as our advantage to create the flip flop table. And when you go on, especially when you reach the counters, you're going to realize that it's important to note that all the possible input conditions for flip flops. All right. So here, the narrator is explaining all this latch. It's really a latch, but it's really the first part of the flip flop. It actually shows you how it works. So if you have a 0 initially at Q, sorry, if you have a 1 at Q, so let's say that Q is 1. If Q is 1 and not Q is 0, obviously, and then we did nothing at the input. So we said S and R to be both 0. So if both are 0, what are we going to get? Knowing what happens with a NOR gate. So let's work on the top one. So if Q, I don't know if you see my cursor. I see my cursor moving. Okay. So if Q is 1, we're going to have a 1 here. And then we say that both, so we're looking at the first condition. So if both inputs are 0, so you have a 0 here and a 1 here. For an NOR gate, ladies and gentlemen, when you have a 1 nor a 0, the output is going to be 0. Agree?
Yes, sir.
Good. So that takes care of the first one. So this is now a 0. So that didn't change. It was a 0 initially. So we have a 0 that is now an input to the second or the lower NOR gate. If this is a 0, that is what's coming from the output of the top NOR gate. And also, R is also a 0. Remember, for OR gate, OR gate, a 0 or a 0 is a 0, right? But for a NOR gate, a 0 or a 0 is a
1, sir.
good. So you have a 1 here. And that makes sense because if you did nothing at the input, and initially Q was 1, and not Q obviously would have been 0, and you did nothing to the input, you realize that the circuit, through its assessment or evaluating of the circuit performance, show you that nothing happens, so Q would not change. What about the situation on screen where we now put a 1 and S and a 0 and R, and Q initially was a 0, which makes not Q being a 1. So if Q is 0, not Q is a 1. Agree? Good. So let's do the cross population now and see what happens. So if Q is 0, we're going to put a 0 right here. And if we put a 0 right here, we know that this was a 1. A 1 or a 0 is a 1, but a 1 nor a 0 gives you a 0. Okay. So we have a 0 here. So you realize what happened? You know realize. Okay. You know realize. Oh, you know realize what's going on. So let's go again. If it's a case, if it's a case, right? So let's do this again.
It's also in.
So let's Q. We want Q to be 0. If Q is 0, everybody hearing me?
Yes, sir.
So Q is 0. So if this is 0, put a 0. A 0 is going to be up here now. Agree? So that's a 0 now. All right. So if Q is 0, not Q must be what?
1, sir.
Good. Good.
So let's start out by
I'll keep it paused. So this is a 1, and this is a 0. So we'll put a 1 from here, and a 1 goes down here, eh? And then we say, all right, we want to set the system. So if we want to set it, it means I've got to put a 1 on S and a 0 on R. Agree?
Yes, sir.
So if we put a 1 here and a 0 here, what happens? What happens now? What's a new output if there anything change? Let's see. So we have a 0 that's coming all the way here, is here, and then a 1 is here. So if a 0 is here, then this originally must have been a 1, right? Not Q must have been a 1. Agree?
Yes, sir.
Cool. Let's see what's going to happen. Now we have a 0 here, and we have a 1 on the set. For a 1 and a 0 going into a NOR gate. 1 or 0 in a NOR gate would have been a 1. But 1 NOR 0 going into a NOR gate is going to give you a 0. So realize, guess what? We change Q, not Q, from its original state of a 1 to now become a what? A 0. Cool. Let's look at what happened down here now. So remember, initially this was a 1. So a 1 or a 0 is going to give you working, you know? Yeah. But a okay, so a 1 or a 0 will give you a 1, agree? But if it's a NOR, a 1 and a 0 is going to give you what? A 0. Good. So you realize in truth and in fact you have now performed the set. You realize that? Because this initially was a 0. That's why I started up and I go up here. But now it becomes a 1. And this originally was a 1, but based on this cross connection, it becomes a 0. So that's how this performs the setting function. Now we can follow it and see how it performs the reset for argument's sake. So let's say that Q was a 1. Oh, I work with me now. Q is 1. That's where we start. So you agree that and you agree with me that not Q would be a 0, right?
Yes, sir.
Good. So now we have 0 coming from not Q, that's going to be at the R, and 1 coming from Q, that's going to be at the S. The condition for a reset is what? S is going to be 0 and R is going to be 1, right?
Yes, sir.
Good. So R is 1. Okay. So we have a 1 right here for R. And what was Q again? Not Q again?
Q was
Not Q. Q was 1, so not Q would have been?
0. Yeah.
Okay. So a 0 nor a 1 give you what?
The 0, sir.
A 0. So you realize that this, which was a 1 initially, now becomes a what?
0.
Ah. And if we do it the other way, initially this was a 1, and now, right.
setting high on a set and a low on the
So this is pretty much what's happening here. So I want you to follow what he's doing. So I'm going to run the video again so that you don't get confused, all right?
reset. Now this particular flip-flop is what's called an active high. In other words, it takes a high to activate that input, or it takes a high to set this flip-flop. There's also ones we'll look at later called active lows that take zeros to activate them. So in this case, there's no inverters out here, there's no bubbles, so it's an active high input. So what we're going to do is a high, low on reset. So a high on set, a high going into this cross-coupled NOR, into a NOR gate, a high into a NOR gate. If you kind of think of it as an OR with an inverter, or with an OR gate, any high gives you a high out, right? So 1 into the OR gate gives you a 1, inverted to a 0. This 0 is getting fed back here to here. 0 or 0 gives you inside, like I said, just an OR, gives you a 0. You invert that to a 1. 1 gets fed back here. 2 highs still gives you a 0. 2 lows gives you a high. And that's our output. So if S is high, reset is low, we get a high on Q and a low on Q naught. Let me put a line here to kind of divide this up a little bit better. So you've got a high on Q, low on Q naught. This is called the set flip-flop. And one note, anytime you set a flip-flop, Q goes high. Okay? Anytime you set a flip-flop, Q goes high. Now that setting may happen with a high or a low here, we don't know. But anytime you set a flip-flop, Q will always go high. So set it, goes high. Now let's change this. Let's say that S now goes to a 0, okay? So we were set, now it goes to a 0. So we've got 2 lows. So we've got a 0 and a 1, 0 ORed with a 1, I should say. 0 ORed with a 1 is still 0 out here. 0 getting fed back here is still 1 out here. 1 still getting fed back, still gives us a 0 here. So nothing changed, did it? Our input went to a low, 2 lows, but we didn't change our output. So basically, if they're both low, Q stays Q and Q naught stays Q naught. This is what's called a hold. And hold means you've stored that information. In other words, we've set the flip-flop, and then we can go to a neutral state. In other words, where we're not setting or resetting at all. It's just holding position. So we're going to keep whatever was there, there. Okay? Next, let's say we reset this flip-flop. And to reset it, we're going to put a high here. So a high and a 0 now. Instead of a 0 here, we've got a 1, which inverts to a 0. 0 is getting fed back here. 0 ORed 0 is 0, which is now a 1. 1's getting fed back here. 2 1s gives us a 0 out. 2 zeros gives us a 1 out. So now you can see that we kind of switched places. That became 0, that became a 1. This is called a reset. It kind of helps you think about it. Remember, like an egg timer or a kitchen timer, if you hit reset, what does it do? It usually goes back to 0. So reset, Q goes to 0. And you can make that another rule. Anytime you reset a flip-flop, Q goes low. Okay? So anytime you set a flip-flop, Q is high. Anytime you reset a flip-flop, Q goes low. Always and forever. Never change. Okay, so I've showed you the set, showed you reset. What happens if this goes back to 0 again? We've got 0 and 1 stays a 0. 0 or 0 stays a 1. 0 or 1 stays a 0. Nothing changed. So that was our hold mode again. In other words, we reset it, and we went back to the hold state. In other words, stay what you were doing. Now, where it gets weird is if we tie them both high. And if we tie this one high and this one high, we've got 1 and 0, which is a 1, which is now a 0. 0 fed back here, still a 0, right? 0, 1, still 0, 0. So we've got both outputs are low. Well, if, like I said at the beginning of this, Q and Q naught should always be the opposite of Q. Well, if they're both low, we got a problem there. So what we do generally is for SR flip-flop, that's a weakness of theirs. It's an undetermined, an unused input. Don't ever do 2 highs on a reset flip-flop. So this is do not do. Do not do that. It's the reason being is, think about it, if you set your kitchen timer again, if you set it for 10 seconds and you're trying to hit reset at the same time, well, you can't set something to 10 seconds and reset it back to 0 at the same time. It's impossible. Next thing we're going to look at is the cross-coupled NAND flip-flop. And what we have to do to make it line up right is we have to put these inverters there. Makes it look a little bit easier. Again, the truth table for this is actually going to be the same. You got SR, Q, and Q naught. But I just want to run through this real quick. The modes are the same. When we hold, so Q and Q naught stay the
So students, just wanted to bring it to your attention. You notice now we're using NAND gates. NAND gates now to make this SR flip-flop. So to use NAND gates to make this SR flip-flop, we have to put them through an inverter. So remember, for the NOR gate, there was no inverter. But for the NAND gate and with the cross connection, as was with the NOR gate, we have to add an inverter to both inputs. All right? So just wanted to bring that to your attention. Please know that the analysis is the same, identical in terms of you're going to get the same behavior, the same truth table as when we use the NOR gates.
the same. This is going to be a reset, so this is 0, that's 1. This is going to be a set, so that goes 1, that goes 0. And this is our do not do. So if we put a high, let's say we put a high on set, a low on reset. Well, we know that Q should go high. So let's look at it. We got a 1 inverts to a 0. 0 inverts to a 1. Well, can't really figure out what's going to happen here because 1 and whatever, we don't know. It depends on what this one is. But I know for a fact that if I put a 0 into an AND gate, the output has to be 0, right? Invert that, since it's the NAND, goes to a 1. Now we can figure out what this one is. 1 and 1 is a 1, which is a 0. 0 fed back here is still 1 out. 1. So see, we set the flip-flop, Q went high, just like we should be. Hold is hold. I'm going to let you know that. Reset's reset. Everything's the same. Let me show you what happens if we go to 2 highs. We got that inverts to a 0. That inverts to a 0. That now becomes a 0. That becomes a 1. The 1. We still got a 0 here. So basically, instead of 2 lows, we ended up with 2 highs. So it's still an invalid condition. In other words, Q and Q naught still can't be the same, but we still have that problem. So it's still a do not do situation with S and R. If I ask you any of these on a handout, it will probably be more, I give you the inputs, you have to tell me what the outputs are. It's not going to be filling out a truth table or anything. It's just going to be, here's the inputs, what's the outputs going to be. So you kind of get it from there. So let's do some timing diagrams. And timing diagrams, if you remember, we kind of discussed them in the notes a little bit, but timing diagrams are a way to represent signals over time. And we're just going to go with the basic SR flip-flop. And I gave you the truth table up here. 2 lows is just holding. A high on reset resets at a low. High on set sets at high. And 2 highs gives you a do not do. And I try not to give you any of the 2 highs in here because we don't want to do that. So for this section right here, we're looking at this section and this section. We've got a low on set, a high on reset. Well, a low on set, high on reset gives you a low on Q. So it's going to be low over to there. Next, we've got a low and a low. Well, 2 lows is just a hold, right? So this is going to reset. This is going to hold, and it's going to hold right there. From here to here, we've got a high on set, low on reset. So a high on set, low on reset is a high on Q. So we're going to go high right here, and it's going to stay high all the way over to there. So it's a set. From there to there, we've got 2 low, so that's going to be a hold. From here to here, we've got a low on set, high on reset, so we're going to reset the flip-flop. And then from there to there, we've got 2 low, so it's going to hold. And then from here to here, we have a high on set, low on reset, so we're going to set the flip-flop. From here to here, we've got 2 low, so it's going to hold. And remember to get this very last bit of it. From there to the end, we've got a low on set, a high on reset, so we're going to reset the flip-flop. So just take it a section at a time. Anywhere you see changes, like here, and we had a change here, then we had a change here, had a change here, 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 and something may or may not happen down here, but you need to look at each one of those changes. So that's just the basic SR flip-flop. Now what they found out was SR flip-flops, regular SR flip-flops are always changing. Anytime you change the input, the output is going to change. Well, that was at a disadvantage for that 2 invalid conditions. So what they did was they invented a gated SR flip-flop. And you sometimes will see these labeled a G, sometimes you'll see it EN, which is enable. You'll see it listed different ways. And what that is, they basically took an SR flip-flop and they added these AND gates over here. There's the output of that one, there's the output of that one. And they tied this one to our enable line. And there's our R, and there's our S. So if the enable line goes 0, 0 on both these AND gates is a 0 out. Well, what happens when S and R are both 0? It holds. So it just holds on. So anytime you're not enabled, in other words, you got a 0 on the enable line, we're just going to hold. Q stays Q, Q naught stays Q naught. When it's high, when it's enabled, we follow just like the regular SR. We got a low and low is just a hold. 0 and 1, high on reset is a reset. High on set is a set. High on both of them is a do not do. So really, we're only going to look for the areas where the enable line is high. So we basically are going to look at it from here to there, there to there, there to there, there to there, and there to there. So we don't care what's going on between. From there to there, we're just going to hold. So the first question we're going to say to ourselves is, okay, what does Q start with? Well, I'm not enabled, right? We're low. And I'm not looking at set and reset. They're turned off. In other words, we're really looking at 2 lows on set and reset when it comes to the chip side of it. So we're really disabled right here. There's no way for me to know what Q starts at. So what we do is we do this invalid, don't know kind of line. You put a little block in there to where you put little hash marks to it, and if we don't know if it's high or low, it could be one or the other. It's going to be something, we just don't know what it is. There's no way to figure it out from our diagram the way it is. Now we can go through here. We're enabled from here to here. Got a high on set, a low on reset, so we know we're going to set that flip-flop, so it's going to be set. From here to here, it's disabled, so it's going to hold. From here to here, it's going to be high on set, low on reset, so we're going to set there. And we've got 2 lows, so it's going to hold right there. We're disabled right here, so we're going to hold. From here to here, we've got from there to there, we've got a high on reset, so we know that's going to reset. And then we've got 2 lows, which is going to hold. Holds right here for 2 blocks because we're disabled. From here to here, we've got 2 lows, so we're going to hold again. Here to here, we're disabled, so we're going to hold. From there to there, we've got a high on set, low on reset, so we're going to set the flip-flop. From here to here, we're disabled, so we're going to hold. From here to here, we're going to be low, we're going to hold from right there to there, right? 2 lows. But then here, what's going to happen is we've got a low on set, a high on reset, so for that second half, remember it's looking at it the whole time, for this second half, we're actually going to reset right there. So always be on the lookout for any changes while it's enabled. And then we're disabled there, so we're just going to hold. So if you're confused about that, you may want to rewind and watch me go through that again. Hopefully it kind of makes sense to you. We'll look at more of these as we go along, not necessarily this particular one, but we'll look at more of these and it'll become a little clearer to you. So, okay, then they decided that enable line itself wasn't enough. We needed something more than just an enable line. So what they did was there was no way to to reset or set the flip-flop until it, we had to get an SR input. Well, there's never a separate one that wasn't tied to the enable line. So what they did was they added this asynchronous SR inputs. And these set and reset inputs, these right here, this one at the bottom is called reset. It's got a bubble on it. The set right here with a reset with a bubble on it. These are what's called active low, and they're only activated when they go low. So you can see up here at the top, I've got a low on set, which actually says activate the set input. So we're going to set the flip-flop. And you remember the rule, anytime you set a flip-flop, Q goes high. So in that case, we set the flip-flop, Q goes high. We don't care what's going on with these. They could be doing anything they want to. It doesn't matter what position they're in. We're always going to set the flip-flop when this goes low. When this one goes low, the asynchronous reset, Q is going to go low instantly. It's not going to wait around for enable lines or anything. It's going to instantly reset. So it goes low. When these are high, we just ignore them. They're not even in play. And then we're back to our regular enabled SR flip-flop. A low on enable just holds. High on set sets it. High on reset resets it. Two highs, don't use that. So this one gets a little bit more complicated. We're going to have to start looking at these sets and resets. And the first thing I see is this set and reset, right? This set goes low from there to there, right? And then I've got this reset line right here goes low from there to there. So I'm just going to kind of draw me some dotted lines. And then the enable lines these are high the rest of the time, so I can kind of ignore those. But from here to here, let me see if I can get a highlighter so you can see a little bit better. So from here to here, we're going to be looking at it. From here to here, we're going to be looking at it because we're enabled. From here to here. And from here to here, we normally would be enabled, but look, remember our set and reset overrides this. So this particular one right here overrides whatever our enable line's doing. So we can ignore that enable right there. Then we've got an enable from here to here. And then we got an enable from here to here. So I only care about these highlighted areas right here. Okay, let me go back to the pen. And what did we start with? That was a question I asked last time, and we didn't know. We didn't know what we started with because we didn't have any way of knowing what it was previous to that. This time, there is a way to figure it out, and we can look at this the set and reset asynchronous inputs, and we know that this set went low right here. Well, remember, if this set goes low, Q goes high, so we know what we start at. We start high right there. And it goes back high right here, but we're not enabled, so we're just going to hold for that section right there. Now we're going to look at our set and reset inputs because we're enabled. And once I've got the highlights, I can kind of just skip from highlighted area to highlighted area. So I've got a high on set, low on reset, so we're going to set it right there. And then we're disabled, so we're going to hold. We're set and then goes low, so we're still going to be set. And two lows is just a hold, so it's a set and a hold. Hold because we're disabled. Now we've got a high on reset, a low on set, so we're going to reset the flip-flop. And then two lows is going to hold. And then here we're going to hold because we're not enabled. And here we've got a reset goes low. Well, remember, if this reset goes low, Q goes low. So you can't go lower than low, so it just basically stays low over to there. And I'll call that a big reset. And then here, we're actually holding because we're still disabled, right? And then here we're set, low on reset, so we're going to set the flip-flop. And then we're going to hold because it's disabled. And here we're going to hold the first half because they're two lows. And then the reset goes high the second half. So hold there, reset right there, and then we're disabled, hold right there. So again, this asynchronous set and reset override the clock, or override the enable line. So no matter what's going on with the enable or the SNR or whatever, if this goes low, we instantly change the output to whatever we went low on. Okay, if you need to look at it again, rewind it, go through it again, and if not, we'll continue on. This is what's called a D-type flip-flop. And
All right, so I notice I don't see any hands, I don't hear no questions, so I'm assuming that you guys are okay with what that so far. Don't find the timing diagram as yet. You'll get some more and sufficient practice with the timing diagram for you to understand clearly what that means. So again, you'll have seen the SR flip-flop, and you saw the introduction to the whole aspect of asynchronous and synchronous, which means the clock. So anybody can tell me what the enable would be like based on what we have discussed so far? What would be the other, in this case, the other name for the enable? So we'll talk about another input, apart from just the SR and the R, the J and the K. What would that be input be?
That'd be the clock pulse.
That would be the clock pulse. Excellent. So we're going to look at the D flip-flop now. And you know the D flip-flop is the one that we say we put an inverter, right? In between. So all this we have discussed already, it's just a matter for it to be brought again to your attention and for it to be a part of your notes in terms of retrieving information as a reminder. So somebody remind me, what's the difference between what is the main thing that makes the D flip-flop different from the JK flip-flop? What is the main thing that makes a D flip-flop different from the regular JK flip-flop? You don't know, really? Right. So remember, with the JK flip-flop, as is, the inputs can be the same. The J and the A and the K can be the same. Likewise, the S and the R can be the same. But when you talk about the D flip-flop, there's a direct intervention to make sure that the inputs are not the same by placing an inverter between the inputs. So now you never have S and R being the same, or more importantly, J and K being the same. Right? And the information that comes in on the D flip-flop, it goes straight to the K. That's what makes it a D flip-flop. The data goes into the input of the not K, sorry, the J. All right, so let's quick look at that.
And basically, it's an SR flip-flop that's been inverted. The S and R has been. So you've got S and R, and you've got this inverter right here, and that's called D. And what happens is they're always going to be opposite. So you're either always going to be setting, you're always going to be resetting. If D is high, you're going to set it. If D is low, you're going to reset it. So so basically, the rule for D-type flip-flop is when enabled, Q follows D. So when you enable the D-type flip-flop, Q will follow D. And you can see that down here. We're enabled here. We're not enabled here, so it just holds. We're enabled, D is low, Q is low. We're enabled, D is high, Q is high. So they pick a highlighter up so we can figure out when we're enabled. Well, we're enabled during this part right here. We're enabled during this part. We're enabled right here. We're enabled right here. We're enabled right here. And we're enabled right here. So any changes that happen while we're enabled, we're going to see. If it doesn't happen during those parts, we won't see it. So to figure out what we start with, no, there's no way to figure out what we start with because the enable is low, so it's holding. Doesn't matter here because it's holding. So we're holding basically an unknown output. So we can just put hash marks in our box. We don't know what that is. It could be high, it could be low. We just don't know. So now we're enabled. Remember, Q follows D. So if D is high and goes low, guess what Q is going to do? It's going to be high and go low. Then we're going to hold because we're disabled. And we're going to follow D. It's going to hold because it's disabled. And then we're going to follow D, so it goes low and goes high. And then we're going to hold because it's disabled. And D is low, so we're going to go low. And you notice we missed the low back here. It didn't go low there. It went low back over here where it's enabled at. So you would miss that if it went low there. Then we're going to hold. Then we're going to go high because D went high. And we're going to hold. And D is high and it goes low, so Q is going to be high and go low. And then we're going to hold. So when it's enabled, during these highlighted parts, might be nice to get a set of highlighters if you want, if you don't already have some. But anytime it's enabled, Q just follows this D input. So go to the next one, and if you need to, rewind and review this one if you need to. This is an asynchronous D-type flip-flop, and we're also adding a new kind of clock to this. And we're adding what's called an edge trigger. And let me show you the different kind of clocks up here. We've been dealing with enable lines that look like either this, which is called a positive pulse. In other words, it's this whole positive area from there to there of the clock. Then they have what's called a negative pulse, which would be the whole negative piece of the clock or enable line. Those are the two without being edge triggered. Then they've added these edge triggered kinds. And if you don't have a bubble, which in this case we don't, this is called a positive edge trigger. And what that does is you've got this clock waveform and it's only on this positive going edge that it's going to enable. So it's kind of like a snapshot, kind of like if you've seen a strobe light, it takes a little like flashes of light. It's only on these positive edges where we're going to be enabled, not the whole positive or the whole negative. It's just on the edges. Then you've got the mouth again, which means edge, and you've got a bubble. The bubble means negative edge trigger. Okay, and the negative edge trigger is the negative going or the downward going clock edge. So it's only on the edges. So when you look at my truth table, you'll see that I've got a positive edge here. I put these little arrows up, meaning it's the positive going clock. Now, if you've got SD and RD, which is our asynchronous inputs, these, remember, override whatever clock you have. So if this goes low, you immediately set the flip-flop. If RD goes low, you immediately reset the flip-flop. So you set and reset the flip-flop regardless of what Q and D is doing. If these go back high, we're looking at our regular truth table. If it's not a positive edge, in other words, it's anywhere but the positive edge, it's just going to hold. On the positive edges, if D is low, Q is going to be low. If positive edge D is high, Q is going to be high. So in this figure one, you can see RD stays high the whole time. So I can ignore that one completely. SD went low just at the very beginning, just to give us a startup condition. Then we can do, again, let me pull up a highlighter. Now we can just look at these positive edges. So really, we only care what's happening there, and there, and there, and there. Just that positive going edge of that clock signal is the only place we're going to look at it. Okay? And change back over to pen. positive edges of these clocks. Bring you a little dial line or a highlighted line or whatever you want to do to indicate that. So the flip-flop, this D type, we can figure out SD went low. If SD goes low, remember, it resets the flip-flop. So we're going to be set all the way over to that first positive edge. On this positive edge, Q is going to follow D. So if D is low right there, Q is going to go low. And it's going to stay low all the way over to here, because if it's not a positive edge, we're just going to hold. Or this is a hold condition. Positive edge, D is low, so we're going to go low and stay low all the way over to there. Right there, D is high, so Q is going to go high. And it's going to stay high all the way over to there. D is high, so we're going to stay high. D goes low here, so we're going to go low. D is low, we're going to stay low. So these are great. I love edge-triggered flip-flops because we're not having to worry about this whole positive pulse or the negative pulse. We can just look at these edges coming down. It's just like little snapshots of the wave, the inputs. Just taking a snapshot, figuring out what it's going to do. Take a snapshot, figure out what it's going to do. So it's a much quicker way of going through these. There's another type of flip-flop called a JK flip-flop. And you remember I said one of the limitations from SR flip-flops was this: anytime you tried to set and reset at the same time, you got an invalid condition. Well, what JK flip-flops do is they overcome that by creating a new mode called toggle mode. And all toggle mode does is it inverts whatever Q was over to a Q naught. In other words, if Q was high, it's going to go low. If Q was low, it's going to go high. So if it was high, it's going to just invert down to low. You'll notice these are edge triggered, positive edge. So if it's not positive edge, it's going to be just a hold. Positive edge, they're both low, it's going to hold. Low on J, high on K is going to reset, and you kind of think of K as a clear. High on J, low on K is a set, and two highs is a toggle. So let's figure out how this actually looks when we do our waveform. And again, we don't have any kind of SD or RD, so we don't know what our initial condition is going to be. We can figure out we got positive edges. So got a positive edge there, positive edge there, positive edge there, and a positive edge there. And so we don't know what this starts at, since we have no idea of knowing what it was before that time. So we just have to do an I don't know, undetermined value. Now here we're going to look right at that instant right there. So J is high, K is low. That's a set. We're going to say set all the way over to there. Now we've got two lows, so that's going to hold. So this is because of J. This is going to hold. Now we've got a high or low on J, a high on K, so it's going to reset or clear. I think of it that way. That's because of K. Now we've got two lows, so it's going to hold. We've got a high on J, low on K, so it's going to set or go high. That's because of J. And here we've got a high on J and a high on K. Remember, that's a toggle mode. So if the output's high right now, it's just going to toggle or inverse to a low. So that'd be our toggle mode right there. So remember, just snapshots of what J and K are doing at those instances, which is great. So I'm going to go on to the next one, and you can rewind if you want to look this over or pause it, whatever you want to do. Go on to the next one. Same thing. I just want to do another example. So again, we have no way of knowing what it starts at, but let me highlight all my positive edges here. So we know where to go. And we don't know what it starts at, so we can do this undetermined box right here. We don't know. Next one, we've got a high on J and a high on K. Okay, that's going to toggle. We don't know what this is right here. So we're going to toggle an unknown. It will flip states, but we just don't know what it flipped from to go to. So we'll just do another box, basically, because we don't know. We have no idea of knowing what that is. And now we've got another edge. So we've got a low on J and high on K. So we're going to reset. Two lows is a hold. Hold. That's because of K. Now we've got a low on J, high on K. We're going to, again, reset it because of K, and you can't go any lower than low, so it just basically stays low. Reset again because of K, and then J is high, K is low, so we're going to set right there. And that's because of J. So again, pause it, rewind it, whatever you need to do, and we'll go on when you're ready. JK.
I see you guys have been fully quiet. Any questions? Or based on my preview, it is not too much of a challenge. And as I said before, don't be too worried about the timing diagram. It is good. It helps you to understand. But we will go over and looking at the timing diagram. The real concept is just to ensure that you understand when we talk about set and reset, what exactly it is that we're talking about. All right? Any questions? Just making sure you guys hearing me.
Sir, the whole thing, sir, I'm gonna get that video. Watch. I'm gonna see it in Google Classroom. I'm gonna see it on YouTube. That easily do that.
Say that again.
So the video, sir, we don't want the link for that specific video, sir, for you watch it again.
Yeah, man. I'm going to put it, it's not in the classroom as yet. I'm going to put it in the WhatsApp and I'm going to put it in the Google Classroom.
All right, sir, respect.
So, what I want to bring from this today is to make you be aware of the three types of flip flops that there are: the J, K, SR, and the D flip flop. You should be able to determine the truth table for each flip flop. We also discovered that the flip flops have additional inputs, reset and the clear. We also learned that we can have synchronous or asynchronous flip flop, which simply means that on a flip flop, the asynchronous does not require clock or timing device. And the clock itself actually behaves as the analogy that we use. It's like a key to the door. If your door is not open, so if the clock is not present, nothing will happen. The clock itself has different way to be analyzed. You can analyze a clock when the clock is going from a 0 to a 1, which is called the rising edge clock or the positive going clock. That's when on the diagram you do not put a bubble on the clock source. But if it's active low, it means that you need a 0, which simply means that the clock is going to now be on the negative going or the 0. So having an understanding, you can actually, from what was presented, see what the requirements are, and that's what the timing diagram is doing. Remember, if the clock poles for the synchronous flip flops are not present, then even if you're changing the inputs, the output won't change. That's because the change of the output is not only now dependent on the JK or SR input, but also on the clock input itself. Clear with that? Clear with that, students?